So we want to use tables here to represent this function, and we want to find all of the important stuff, right? We're trying to find, asymptotes, intercepts, relative extrema, inflection points. We want to ask if there's any symmetry. Yesterday, we started to look at this example. Did we finish talking about the symmetry? I can't remember. Right, what did we say about the symmetry? We said that this one had odd symmetry. Okay, how come? There's two reasons we can say that. This has odd symmetry because we can apply the test, first of all, right? We can just directly apply the test. F of negative x would equal, on the top, I'd get a negative x. On the bottom, if I plug negative x in, well, when I square it, the negative goes away. So I just get x squared minus 3. And isn't that equal to negative? That just equals negative the quantity x over x squared minus 3, which is negative f of x, right? And so we can see then that this is odd symmetry, right? Because f of negative x equals negative f of x. There's another way we can do this, though, too. This is a sort of a trickier way that is going to be easier to apply sometimes than having to go through the whole process of applying that symmetry test. On the top, we've got a polynomial that we know is odd, right? On the bottom, we've got a polynomial that we know is even, okay? When I have a rational function like this, where polynomials on the top and the bottom, they don't even have to be polynomials, just a function where I've got an odd function on the top and an even on the bottom, how does that work out? Well, we've got rules for that are similar to sine rules. If I have an even divided by even, that gives us an overall even, right? If I have an odd divided by an even, or an even divided by an odd, that gives us odd. What do you think odd divided by odd equals? Type it in chat. Yeah, it's even. Good. So you can treat evens like positives and odds like negatives, and this works just like sine rules then, okay? How come you make the evens, well, I don't know why, I just do that. You make the evens positive and the odds negative, and it works the same as regular sine rules. Either way, though, we get even symmetry, okay? The domain is all reals, so now we can just start doing some calculus maybe, right? Okay, so let's differentiate here. Y is equal to x squared over x squared plus 3, so let's calculate y prime. Y prime. Kyle, help me out with this. Let's differentiate this. What rule are we going to use to differentiate this? Quotient rule. Good. So what do we get?
X squared plus 3 times 2x minus 2x times x squared divided by x squared plus 3 squared.
Okay, good. So, and I'm going to do it, you're right. I'm going to do it as low d high minus high d low. Derivative of the bottom would just be my 2x, good. And all divided by the bottom squared. Okay, so if I distribute the 2x, I'm going to get 2x cubed plus 6x minus 2x cubed. So the x cubed terms cancel, and I get 6x over the quantity x squared plus 3 squared. Everybody give me 1 to 5 on that. Everybody. I'm not hearing from everybody. Okay, all right, good enough. So there's our first derivative. Let's go ahead and find derivatives of the first, or find critical numbers based on our first derivative. So are there any places, give me thumbs up or thumbs down, are there any places where the first derivative is undefined? Thumbs up is yes, thumbs down is no. Okay, again, are there thumbs up, yes, thumbs down, no? Are there any places where the first derivative is undefined? You can just type in chat yes or no too. Okay, good. Good. The bottom is never zero, is it? Where is our first derivative equal to zero? Y prime equals zero at x equals what? Okay, I'm seeing lots of zeros. Everybody agree? The numerator is zero when x is zero. Okay, so we got critical numbers. Let's calculate the second derivative. And so we can use this, we'll use that form right there, our simplified quotient, to calculate the second derivative. And what am I going to get for my second derivative here? Daisy. Gonna have to do another quotient, aren't
I? Yeah.
Okay.
So it would be 6 times the denominator, right?
Okay, good. So I get the quantity x squared plus 3 squared times the derivative of that, which is 6. We'll go ahead and put that out front. That was smart. Minus.
Minus 6x times. You have to use the chain rule.
Good.
So,
Yep. Got to use chain rule. Good.
2 times the quantity x squared plus 3. And then it's just 2x.
There you go. Good job. Okay. All divided by the bottom squared, which is just going to be, if I square a square, I just get fourth power, right? So on the bottom, I'm going to get x squared plus 3 to the fourth. Okay, so now here's where we got to be a little bit careful, because if you're not doing this efficiently, you can make a heck of a lot of extra work for yourself here if you're not careful, right? There might be a temptation to, for example, especially among overachieving math students, to expand all this stuff out and make one big polynomial on the top. Is that a good idea? Probably not, by the way I'm asking you, but why is that maybe not a good idea? Let me ask you this. When all the mathematical dust settles here on this process, and we're trying to use our second derivative, we're going to try to find zeros of that second derivative, aren't we? Right? So to find zeros, what form do we want the top and the bottom of this rational function to be in? Yeah, exactly. We want them factored, don't we? Right? So because we want them factored, we're always going to be looking for opportunities to factor out common factors, right? And there are other reasons that that's useful as well. We're going to factor out common factors because we might be able to cancel common factors then, top and bottom, which makes the whole thing simpler. So can we identify some bases that we can factor out of the top? Let's focus on the top. Well, yeah, look at this. And we've got these x squareds plus 3 popping up everywhere, right? So there's an x squared plus 3 and there's an x squared plus 3. I could pull those out front. Looks like I could take a 6 out front also, right? So then I end up with, if I factor out a 6 and I've got an x squared plus 3, I've got that base squared and that base to the 1. What can I factor out then? What power in the numerator of the base x squared plus 3 can I factor out? Just hold up fingers. Can I factor out a 1 or a first power or a second power? Right? If I've got that base squared in the first term and that base to the first power in the second, Yeah, okay, I can only factor out the least common power, right? So I can only factor out to the first power. I can factor out an x squared plus 3. And then what's left behind when I do all that stuff? So here's my minus sign. What am I left with from the first term? Well, it looks like that 6 goes away, and I'm factoring away one of those powers, right? So I'm left with, in that first term, I'm left with an x squared plus 3. And I don't really need the parentheses anymore, right? Because nothing's being distributed and it's no longer being taken to a power. What about the second one? Second one, I'm factoring out that 6, and I'm factoring out that entire base, that factor, and I'm left with x times 2 times 2x. So I'm subtracting 4x squared. And then on the bottom, I've got an x squared plus 3 to the fourth. Well, one thing we can see is, look, we've got a common factor on the top and the bottom then that I can also cancel. I can cancel that guy and make that into a 3, right? And so I end up with y double prime equals 6. That's gone. I could compress this all into a single factor. I get 3 minus 3x squared divided by x squared plus 3 quantity cubed. And I can even pull another 3 out front if I want to, right? So I get 18 times 1 minus x squared divided by x squared plus 3 cubed. Okay, so do I have any values of x where the second derivative is undefined? Not that we care so much about that, but are there any? Thumbs up, thumbs down. Is the second derivative undefined anywhere? No, it's not. Good. Where is the second derivative equal to 0? So y double prime equals 0 when that factor is 0, right? That factor is 0 when x squared equals 1. So what are my values of x? Type it in chat. What are the values of x where my second derivative is 0? Okay, good. I'm seeing plus or minus 1. Okay, so we got a bunch of critical numbers. What else could we do here? Well, let's look at this rational function and let's see if we can do some asymptotes on this also. Okay, there are no vertical asymptotes, agreed, because there's no zeros of the denominator, but horizontal asymptotes. So what's our horizontal asymptote going to be? I have to take a limit as x approaches infinity, right? So I'm taking the limit of x squared over x squared plus 3 as x approaches plus or minus infinity. Okay, think back to our discussion earlier of infinite or limits at infinity. What is the limit of x squared divided by x squared plus 3 as x approaches plus or minus infinity? Type that in chat for me, please. And you don't have to do any algebra here. This is one where we can just write an answer down for this. Like even on a test. I mean, this is one that we just know based on our rules. What's that limit? Okay, let me hear from everybody on this. And if you're not sure, just give me a question mark if you're not sure, and we'll talk about why. right? Okay, so I agree. It's 1, but let's talk about why. So let's just do a brief review. If I go back a couple slides, remember this, right? How do we find limits at plus or minus infinity for rational functions? Polynomial divided by polynomial. Remember these rules. If the degree of the numerator is less than the degree of the denominator, so the bottom polynomial is a higher degree than the top polynomial, then the limit is 0, right? If the degree of the numerator and the denominator are the same, then the limit is equal to the ratio of the leading coefficients, right? And then finally, if the degree of the numerator is greater than the degree of the denominator, so the top polynomial is more powerful than the bottom polynomial, there are no horizontal asymptotes, okay? The algebra for that, I don't want to get too bogged down in the algebra, but if I just took this very, very briefly, I'll do this super quick. Whoops. Oh, that's bad. Okay, what could we do? What would our algebra be on something like this, right? All I'm going to do is I'm going to factor out an x squared from the top and the bottom if we really wanted to do the algebra. We don't have to. Those cancel algebraically, and so this is just equal to the limit of 1 over 1 plus 3 over x squared as x approaches plus or minus infinity, and 3 over x squared, as x gets huge, that term right there in the bottom just approaches 0, so I get 1 over 1, right? In this case. Does that make sense? Is that ringing a bell? Okay. All right, so we got a lot of info then. We've got a ton of information. Let's go on, and I'm just going to, maybe I'll copy and paste the values of our derivatives, and we'll go make a table out of this, but this is too messy. So let's go to, whoops, that's not what I want. Let's go to another page. So there's our first derivative. We'll grab that one. And we'll just go to another page and we'll paste all this stuff and make our table. Oh, how'd that get in there? How did that get in there? I don't know how that showed up. That must have been a little bit of an oversight, I guess. I don't know. I apologize. I'm not sure how that happened. But anyway. Okay. Okay, so there's our function, our first derivative. and our second derivative, right? And then we had our limit. I'll just write that in. Okay, so let's make a table out of all this. So our domain, we said, and this is where, you know, I really focus on this part, right? This is the part where I want you to get good at, is using these tables. So our domain went from negative infinity to infinity. We can show the limit on here. Whoops. The limit as we approach negative infinity was 1. The limit as we approach positive infinity is 1, right? So that's giving us our horizontal asymptote. We also had, remember, we had odd symmetry. Okay. And our critical numbers. 0 was our critical number for the first derivative. It was a 0 for the first derivative, so we get a horizontal tangent. And plus and minus 1 were our critical numbers for the second derivative, the zeros of the second derivative. Okay, what should we do? Type in chat. What's one thing I've got to do here? What do I have to do on my table here? Say it again, Seth. Okay. Test points, like tell me specifically, what x value should I plug into which derivative here? Okay, well, we can kill two birds with one stone here, right? Because we need to know inflection point, so we need to know whether those zeros of y double prime are transitions, right? I've got to evaluate the sign of the second derivative around my zeros. Okay, but I also need to know where the extrema are, and so I also need to know what's going on at x equals 0, right? So the second derivative test does double duty here. I can evaluate the sign of the second derivative at y double prime, and it does two important things for me, right? So what happens there? If I plug 0 into my second derivative, you guys tell me in chat, please, if I plug 0 into my second derivative, is y double prime positive or negative? Just type in a plus or a minus. If I'm plugging in 0, yeah, everybody agree it's positive, isn't it, right? I'm just getting 18 times 1 divided by 3 cubed. Yeah, so I'm getting positive. Okay, that's important. If that's positive, then that's telling me that this is a minimum, right? So there's one thing. Now I've got to pick some test points below -1 and above +1 to see if these are inflection points, because I'm looking for everything on this. If I weren't looking for inflection points, I wouldn't care, but I am. So let's try a value like, how about, oh, I don't know, like what about negative 10? If I plug negative 10 in, positive or negative, please? Actually, let's do positive 10. I want to do positive 10. Okay. So f double prime of positive 10 is what? Positive or negative? Give me a plus or a minus. Everybody? Okay, I'm getting lots of negatives. I agree. I end up getting negative over positive is negative. And so sure enough, this has to be an inflection point, doesn't it? Okay, can you tell me what am I going to get there? Negative or positive? Well, obviously it's going to be negative, isn't it, if I plug it in? How could I have known that without even having to plug a point in at negative 10? On the top, you mean, right? For y, oh, okay, good. For y double prime, it's even. You're right. For y double prime, we get even symmetry. Okay. My original function has odd symmetry, right? Everybody agree? Right? Is that helpful to me at all? Right. Okay, that's okay, good. Okay, so then if I wanted to, for example, let's say we want to put in some points here. We want to make this thing, we haven't done this for a while, but let's actually find some points so we can anchor this to the XY plane and get a more accurate graph. If I plug 0 in into my function, what's the Y value? Here's my function. 0, right? I'm going to get 0 divided by 3, which is 0. What if I plug in 1? What do I get? 1/4. So what do I have to get when I plug negative 1 in? Don't even bother plugging it in. We have odd symmetry. So what's it have to be? Oh, no, we have even symmetry on this one. Why did I write odd symmetry down? What the heck happened there? Did I do? Oh, no wonder. This was a different function, wasn't it? Right? That one had odd. Yeah, no wonder this messed me up. So this guy right here, this has even symmetry, doesn't it? I wrote down odd. But it should be even because I've got an even function divided by an even function. Right? So I know I've got folding symmetry about that y-axis. So everything that's happening to the right of 0 has to be mimicked on the left, right? So I should get back, I know I have to get back 1/4 because when I go 1 to the right, I have to have the same output as I do at 1 to the left. Okay, and this makes sense now. This was kind of perplexing me a second ago. If that was odd, we wouldn't have expected this, but I should have everything duplicated on the left side. So if that's negative, that's negative. It's literally like I'm just folding this page right around that vertical line, and I should get the same values in y prime, actually y and y double prime, right? Does that make sense? Everything's going to look, everything on this y prime, or the y row and the y double prime row has to look the same. The concavities have to be the same, don't they? Right? If I'm going to fold this thing over, if it's concave up to the right of the x-axis, it has to be concave up to the left of the y-axis, sorry, also, okay? So we could kind of finesse our way through that. Do you have to? No, you don't. You don't. You can just fill in the table and not even use the symmetry if you don't want to, but it's there. Okay. All right. So what's this thing look like then? Well, at 0, 0, we know we have a minimum. Over here at 1, 1/4, we have an inflection point. So we'll just say that's 1/4. And we have a horizontal asymptote at 1. So we'll make that 1, and that's 1/4. Right, so there's my horizontal asymptote. Then doesn't this thing have to do this? It's bowl shaped up. That's where it starts to become bowl shaped down, and then it's asymptotic. And I've got folding symmetry, so I know it's doing the same thing on that side. Okay, we good? 1 to 5. All right. So then how would we answer all this stuff? What's the domain? Well, domain, that's pretty obvious. That's just negative infinity to infinity, right? How would you put it? Oh, lots of stuff, right? Even functions are always symmetric about the y-axis. So it'd be that answer right there, wouldn't it?
I don't know how much you just said there, but probably for like 15 seconds, we can only hear probably a quarter of what you were saying.
Oh, man, I wonder why it's doing this. Okay, so I didn't say anything too profound. I'm just filling out. In Math Excel, you're going to get asked a bunch of questions for each of these functions that you're doing this curve sketching stuff, right? You're trying to analyze these curves. So all reals for the domain. It's even symmetry, so it has to be symmetric about the y-axis. What's the derivative? Well, we did the derivatives, right? You would just enter the derivative functions right there, okay? And do they have to be, is there only one way you could write them? No, it's not. I mean, like, for example, on this guy here, if I had left this as 18 minus 18x squared, that would have been fine. I didn't have to factor out the 18 when I input the derivative, right? Those little nitpicky things don't matter. So first and second derivative, are there any critical points? Yeah, the critical points occurred at x equals 0 on that one, right? Let's see, we had a local minimum or maximum at the point 0, 0, right? They want that as an ordered pair. So we had 0, 0. Oh, whoops. And we had a minimum, right? The local maximum, there was no local maximum. So it would have been that. Where does it increase and where does it decrease? Let's go back to our table for a second. So that is a first derivative issue. Well, I know that if I don't even have to use the first derivative test here, if this is a minimum and there's only one critical number, then I know it has to be negative every place to the left of 0 and positive every place to the right. Agreed? So then it's going to be increasing on the interval from 0 to infinity and decreasing on the interval from negative infinity to 0. So increases on, what did we say, 0 to infinity. And decreases on the open interval, negative infinity to 0. So we choose option A. Everybody give me a 1 to 5 on that real quick. Does that answer make sense? How we did that? Okay. 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 It looks like we're pretty good on that. Were there any inflection points? Yes. And what X values? The inflection points were at -1. We're supposed to use commas here if we have multiple. So it was -1, comma 1. Those were the two X values. Identify where the curve is concave up or concave down. Okay, well, then we just go back to our table for that one. And it looks like we look at the second derivative row, it's concave up between -1 and 1, and it's concave down everywhere else, right? So it's concave up on the intervals. We said -1 to 1, and those are open intervals, right? At the zeros, those are transitional points. So it's between -1 and 1, and it's concave down on the intervals -infinity to -1, and we want to use commas to separate intervals. It tells us to do that. Or 1 to infinity. So I don't know why that's filled in. It should be that one. Vertical asymptotes. There were no vertical asymptotes. Horizontal asymptotes. Yeah, it had one horizontal asymptote, and that was y equals 1. Okay, so far so good. Give me 1 to 5. Asymptotes, so slant asymptotes, no, we didn't have any, and I think that's it. Oh. This is different function, so I don't know what's going on here. You would pick the one that's the right graph. None of these apply. Absolute maximum, absolute minimum. Is there an absolute maximum? No, there is no absolute maximum, right? Was there an absolute minimum? There was, right? There was an absolute minimum at the point 0, 0. That is the absolute lowest point, any domain you could possibly choose. That's the lowest point, right? So an absolute minimum in this case had the value of 0. It occurred at x equals 0 because the coordinates were 0, 0, right? Okay. All right. Good. Good. Okay, let's do another one here. We won't get through it. I mean, this one will go faster though. Now that we've been through one of these things, we can charge through this one a little. No, it's not very good, but can you hear me well enough if I leave it on there? Okay, I'll just do that. I'll just leave it on that one.